James founded Close Comfort, a Perth startup, to commercialize a new kind of air conditioner. Their products could help eliminate greenhouse emissions caused by air conditioners, reduce peak loads on the electricity network, and also reduce electricity bills. James has worked on the ground in low-income countries for 25 years. He's also received international awards for his teaching and research, including the world's preeminent prize for robotics research, the Joseph Engelberger Award in 1993. So without any further hesitation, I would like to introduce James Trevelyan to Send Presents tonight, and please welcome him.
Thank you very much, Ian. This is going to be an interesting experience because I think I have to look sideways to see my presentation. And I do admire the way that you've got this all together in such a short time. It's amazing. Well done. And particularly thank you to Alistair in Melbourne, who's going to be manually working our way through the presentation. And Alistair, I've got my mobile set up here so I can have a quick look and see what everybody else is seeing. So download pretty quickly.
James, maybe I ask you a few questions. When did you start Close Comfort? And
we started in 2007.
Right.
Yeah, long time back. And it was mainly because you can, government R&D, tax concessions and things like that, the formalities of buying and selling, and it was also to keep the work independent of the university, because actually this work is, although I'm an Emeritus Professor at the university, we decided to keep the work entirely separate from my research. My research is actually on what engineers really do. And that work started in Pakistan.
Right.
And that was why I got exposed to pretty hot weather, but wonderful family and wonderful mangoes. Yes. The mangoes in Pakistan are to die for.
Yes.
Definitely. So, and you nearly do die because when the air conditioning goes off at 3 o'clock in the morning and you're lying in bed sweating, wondering when the power is going to come back on, that was what led to the idea of Close Comfort.
Because you
an
felt
air conditioner that would run on a battery through the power cuts.
So necessity was the mother of invention.
Necessity was the mother of invention. Yeah.
Right. So we can bring this technology into the first world now because we're seeing the need to decarbonize, which would result in lower electricity demand, etc.
Well, I'm going to talk a lot about the third world, or what we call the third world, which is rapidly becoming the first world.
Yes.
Yeah. So I think, is that long enough? Do you think everybody's downloaded?
I think
okay.
So
the first slide, actually, you saw a beautiful picture of the Milky Way taken at night by an engineer who worked for me, Richard Watson. And he produced that beautiful photograph. But the title of the talk is Air Conditioning Towards Net Zero 2050. And I think Ian has introduced it well enough for all of you. So we go to the second slide. You will often see photographs like this, and they're not a distortion of reality. I have literally been through cities where I have seen walls containing hundreds of split system air conditioner outdoor units that tower up into the sky. And you can visualize to yourself, each one of these is producing a blast of warm air that's typically 10 to 12 degrees above ambient. So that warm air goes up the side of the building. And yeah, you're right. The heat exchangers higher up the building have to work even harder because they're using the warm air that's belched out by the air conditioners down the bottom. Go to the next slide, which shows a sort of satellite thermographic picture of Sydney. And this is what we mean by an urban heat island. So our cities are hotter than the surrounding areas. And interestingly, perhaps not so, when you think about it, it's pretty obvious. On a really hot day, they are much hotter than the surrounding countryside. Why? Because everybody turns on air conditioners. And air conditioners generally have a nasty characteristic that once they go from running intermittently to flat out, and this particularly affects the more modern style of air conditioners, inverter air conditioners, they're really designed to be efficient at a modest temperature. Once the temperature difference gets really high, gets really hot outside, they operate in a much less efficient zone of their operating envelope, and so the power consumption rapidly rises. Of course, there are many other effects as well. The fact that there are fewer trees, that streets are paved with materials that absorb heat and don't emit it very well. But the net result is, if you think about Sydney, The temperature in the surrounding area might be 30 degrees centigrade. It can be up to 40 degrees centigrade in some of those hot areas. But if you think of like a city like New Delhi, where the surrounding temperature might be 42, 43 degrees, then the temperature in the city, many parts of the city, is up 48, 49. And even at midnight, you'll find that the temperature in apartment buildings is typically 40 degrees, 42, 44 degrees. Very uncomfortable. Now, here are some of the health implications. This slide shows excess mortality in extreme temperatures. And this information is from a paper in the Lancet. The references, by the way, are given on all on the slides which need them, so you can look it up yourself. But the point here is quite simple, that at temperature extremes, excess mortality rises. What do we mean by excess mortality? In essence, it's deaths that occur because of the influence of the high or low temperatures. Now, there's a big difference between the effects of high temperatures and low temperatures. Low temperatures tend to manifest themselves as extra stress on the cardiovascular system, increased probability of diseases like influenza and pneumonia. So typically the deaths will show up after a sustained period of cold weather of maybe 2, 3, 4 weeks. With heat, it's very different. After 2 or 3 days of successive days of high temperatures, many people, particularly older people, keel over and have to become hospital admissions, and unfortunately many of them die. In Paris, in somewhere around 2003, I think it was, there was a heat wave, and on the second and third days of that heat wave, 16,000 additional deaths occurred, and the hospitals were just completely overwhelmed. They haven't had that since, because there's been better information available to older people, particularly, to drink more and so on and so forth. But this problem is becoming more and more frequent. In Seville last year in southern Spain, the temperature in some parts of the city reached 50 degrees centigrade, and there is no protection from the heat for older people there. The next slide shows an image from a wonderful website, earth.nullschool.net. And this image is essentially a heat map at around midnight. And that image is showing in colors what the temperature feels like. The yellow areas, it's around about 33 degrees centigrade, 80% humidity. And that feels like 46 degrees if you're in it. If you've been in those conditions, you'll know what I'm talking about. And the effect of the high humidity, of course, is it shuts down your body's transpiration system, both inside the lungs and on the skin. So you get a rapid rise in apparent temperature. And these conditions occur pretty regularly through the summer months across South Asia, the Middle East, but it's in South Asia where we have this massive concentration of people, around 2 billion people living there in Bangladesh, India, Pakistan, and Sri Lanka. They're not all exposed to this heat all the time. But one of the things that I learned by living there through these summer months is that a large proportion of the population don't get regular sleep. Even those with air conditioners, most of them can only afford to run them without a generator. And that means with the load shedding that the power goes on and off. And so sleep goes on and off through the night. And after a period of weeks, people get more and more irritable, the exhaustion. So I've been asked what slide number it is. I've got no idea what the slide number is, but the next slide we're on is Warming Predictions, IPCC 2018. Now, this comes from the IPCC report issued in October 2018. And it basically shows you what the projected temperature rise is going to be. And they actually give 3 different scenarios. Essentially, what they're saying is that this assumes that the world is going to manage to achieve net zero emissions somewhere between 2045 and 2055. Now, I've been actually pleasantly surprised that so many countries have signed on to this recommendation. And so definitely progress is being made. And I say that because the message has been received not only by a number of governments of leading countries around the world. There's certain well-known exceptions, but particularly by the finance industry. And the finance industry increasingly is driving the decision-making, which is going to make or break the efforts to achieve this target. Certainly some very promising noises. Now, the next slide shows two additional lines, red lines. That shows the extra half a degree warming by the end of the century that we will get unless we do something about air conditioning. And the present trajectory that we're on is not very promising. There are some good signs and there are some new ideas around, but not on a large scale. What is driving the use of air conditioning is, of course, the warming climate, number one. Number two is urban migration. So people have migrated from countrysides to urban centers across South Asia, across Southeast Asia, and many other countries. And they're now living in apartment blocks which get progressively hotter and hotter and hotter as the climate warms. So the kind of escape routes that people used to have to avoid the heat are no longer available. When you're living on the top of an apartment building and the roof is baking hot, you don't have anywhere else to go. And temperatures have reached the point where serious mortality issues start to arise. And that's why people are using air conditioners, because you need it to stay alive. And this is a very simple illustration. It's called Countdown to 1.5 degree warming. All of this is on the assumption that we manage to keep the climate warming within 1.5 degrees. And that of course is questionable, as is the data, because there's a lot of uncertainty about these estimates. But in essence, that clock is ticking by about 1 minute per year. So in a sense, it's like we're 11 minutes to midnight. And you might say, oh, wow, 11 years to go. That's not very good. So all of this, we're basically working on the assumption that we will be able to make significant cuts to greenhouse emissions rapidly. And the next slide shows that. This again is reproduced from the IPCC report, and you will see there the steady rise in emissions up until 2020 this year, followed by a steep decline. Gratifyingly, emissions last year appear to have decreased for the first time significantly, and obviously there's going to be a significant decrease this year with the economic activity reducing. And so maybe we can keep going in the same direction. Let's hope so. But the point is, as I'm sure you'll understand, is that we have to have viable solutions. And we've got a lot of solutions out there ready to go, but we do need some new ones, as I'm going to explain. So the most obvious way to get emissions down is simply energy efficiency. And what I've shown here on this slide entitled Energy Efficiency, which is, sorry, I have to lean over to see my screen. Slide number 10. We used incandescent light bulbs. Of course, they took over from oil lamps and kerosene lamps, gas lamps. In the 1950s, we saw the introduction of fluorescent tubes, which significantly reduced the energy requirement for the same amount of light, even though many people didn't like that particular kind of light. In the 1990s, we had low power fluorescents, reducing the power still further. And now, of course, we have LEDs, which mean that we can reduce the power still again. So you can see these kinds of energy improvements, energy efficiency improvements are nothing new. We simply need to extend them much further and wider than we have done before. Very much an engineering related issue. But certainly there's a lot of potential energy efficiency improvements that are out there. In the past, engineers have had to justify these changes, introducing these new technologies on the basis of economics. You have to present a business case to get a business to make these moves. But now, increasingly, businesses are telling their engineers, go and do it. Just find a solution. We want our emissions to come down to zero by 2050, which is a very encouraging sign. Now, the next slide, 11, is from a paper which provided much of the data behind the IPCC reports for residential air conditioning. And basically what it shows is that the dominant energy demand, as you would guess from that map that I showed a few slides back, is going to be from South Asia and Southeast Asia. These are the areas where large populations are living in hot and humid climate conditions. And of course, it's that humidity which adds significantly to the amount of energy that you need in order to run an air conditioner. You've got to get a lot of the water vapor out of the air in order to be able to reduce the temperature. And of course, there are many assumptions behind this prediction. And some of those assumptions are questionable, and maybe we could talk about those in the Q&A session towards the end. However, we need to understand that we desperately need to do something. And in response to that, the Rocky Mountains Institute has teamed up with the government of India and announced in November 2018 the Global Cooling Prize. This has $3 million US dollars worth of prize money, and I think a little bit more has come in since. And the idea is to choose what turned out to be 8 finalists who will demonstrate new technologies. The aims are essentially to, I'm going to come to that in a moment. Sorry, I should really address myself. I keep looking at the screen and I forget what's on the slides. In essence, this is what's important to understand is that air conditioners produce 2 kinds of greenhouse emissions, indirect and direct. Direct emissions are caused by the refrigerant gases that leak out of the air conditioners during the course of their lifetime, and particularly when they're scrapped at the end of their life, because as I understand it, typically only about 5% of refrigerants are collected worldwide at the moment. So we work on the assumption that those refrigerants are discharged into the atmosphere. And some of them are extremely potent greenhouse gases, thousands of times more potent than CO2. And so the estimates are that if we don't control this, that in the direct emissions from refrigerant gases would eventually outstrip the indirect emissions. Indirect emissions arise from generating the electricity that is used to run the air conditioners. And of course, the reason why we call them indirect is because the emissions appear at the power station rather than at your air conditioner. It's not the hot air that comes out the warm side of the air conditioner. It's the CO2 that goes up the smokestacks of coal-fired power stations or the emissions from gas-fired power stations and so on. And of course, we assume that gradually more and more renewable energy will be used. And so consequently, the magnitude of these indirect emissions will decrease proportionately over time. So this graph shows that. And it draws attention to the Kigali. It's actually not the Kigali Protocol. It's actually called the Kigali Amendment to the Montreal Protocol, 2016, where most of the world's leading countries agreed to, have not necessarily signed it into law yet, but have agreed to reduce the use of high greenhouse potential refrigerant gases, phase them out. And the phasing out occurs in developed countries from 2018 through to 2037. In low-income countries, in the developing world, the phase-out doesn't commence for another few years, starts in 2028 and goes through to 2047. And yeah, you realize that air conditioners typically have a life of 10 to 20 years. So many of the air conditioners that are using today's refrigerant gases will be still in use by the time we get to 2040, 2050. So this is a very good step because it got through the political process, with much less fanfare than the Paris Agreement. There's been much less controversy about it. And the world is definitely on track to try and do something about this. It's not signed into law yet, but definitely the major refrigerant manufacturing companies are trying to push things along in the right direction by providing training for engineers and all kinds of support. So there are 2 questions that come up. One is the cost of the new refrigerants. The other is flammability. So some of the refrigerants that we will need to start using are flammable gases. And so this restricts the size of the units that they can be used in. They've got to be used in small units in order to make sure that these are small sealed units, which will be, in fact, in use today. we'll see many, many more of these units because of the need to use these refrigerants. At the same time, as I said, we should expect to see significant drop in the CO2 emitted by power generation stations. This is a desirable trend. It's not an actual forecast, but basically the idea is that by 2050, we need to be producing electricity without significant CO2 emissions, one way or another. And now the global cooling prize, essentially there, what the idea was to come up with a drop-in replacement for a split system air conditioner. And the idea is that this split system air conditioner will have 5 times less impact on the climate and should not cost more than twice the existing units that are already out there on the market. They've chosen 8 finalists across a spectrum of conventional and unconventional technologies. I'm not going to go into the details yet. I'm quite happy to answer questions on those, but please bear in mind something which we have to understand with new technologies. While new technologies are always exciting and interesting, typically they take around about 30 to 40 years from the first public demonstration to the point where they're widely in use. Yeah, you got it. We don't have enough time. We have to use existing technologies to get there. New technologies may help, it may come along and help, but they're not going to be enough on their own. So what are the options? Can we get to zero emissions by 2050? I think so, yes. I'm an optimist. It's going to be achieved with many different measures, all of them complementary, working in the same direction. How am I off for time, by the way? Good. They've got a thumbs up, so that means I'm okay. Obviously, reducing the global warming potential of the refrigerant gases is going to help. But as I said, it may come too late. Reducing the carbon intensity of electricity generation, that's going to help too. But ultimately, we have to use less energy to do our air conditioning. That's what's going to make a difference. We have to be much smarter about the way we use air conditioning. So I'm going to talk about several options: vernacular architecture, passive solar design, rethinking the home. Bear in mind that a very large proportion of this growth in air conditioning demand is residential air conditioning, because people need it at night for sleeping. We have to rethink what we mean by comfort and find new ways to achieve comfort. And I will present a strong argument that localizing comfort is a very powerful solution pathway. Not the only one, but a very powerful one. So what do we mean by vernacular architecture? The architects out there, I'm sure, will know. This is a wind house. It's a very famous wind house in Iran, and I was very privileged to be able to stay there. And they proudly show you the 20,000 rial note in Iran, which actually carries a beautiful drawing of this wind house. The wind house has a tower structure, and the idea is that you control the movement of air through the building, air which is cooled by the water in the pond that you can see in the foreground there, and is drawn up through vents that you can control. Using this kind of architecture does require a lot of experience. You need to know how to use it effectively. And furthermore, it doesn't result in cooling of the whole structure. You also need to know how to plan your life, and different things happen in different parts of the house at different times of the year. It's not a solution for everybody. It's quite expensive too. Now here's another solution. That this is in Australia, Kupapidi. You build your house underground and make use of the fact that the temperature underground is generally pretty modest and pretty much comfortable all the year round. But again, there's not many places where you can do that, and you have to be very sure that you're not going to get floodwaters. And this is what people are increasingly facing in city after city after city. Walls of apartment buildings stretching to the sky with, you guys, the external units of split air conditioners. There's another factor too, which has not been discussed or only been briefly discussed, and that is affordability. As Ian said in the introduction, I spend quite a bit of time in low-income countries, particularly Pakistan, where my wonderful family and my wife were born and raised. And there's this general assumption that everybody in low-income countries is going to become rich. And there are major questions we have to ask about that assumption because, as Mahatma Gandhi said a long time back, when asked, is it that your ambition for everybody in India to have the same living standards as we in the Western world? And Gandhi said, well, of course, that's ridiculous because the world wouldn't last very long because simply we'd run out of materials in a very short time. So we're not just talking about one issue here of global warming. We need to think about all aspects of sustainability. And in essence, we have to change from technologies which have assumed an infinite planet, infinite amount of water, that you can discharge anything you like when you like, and that all the materials are infinitely available at any time you want them, to one where we have a closed system. And it's taking a while for engineers to respond appropriately to that. So we have to think seriously about this issue of affordability. So just to give you some idea, because I'm sure you know that I developed personal air conditioning technology. Although conventional air conditioning is available in around about 7 or 8% of homes in India and Pakistan, similar countries, only about 3% can afford to run them on a sustained basis because of the electricity cost. And that's of critical importance because the running costs are by far the largest investment that you make when you buy an air conditioner, if you're going to use it at all. In fact, I might tell you that in Pakistan, often when you go to the air conditioning shop, the first thing you see is the big diesel generator, and you won't get continuous air conditioning without it. If we can reduce the amount of energy that we use for air conditioning, then not only, of course, is it cheaper, but a far greater number of people can use it. And that's of really critical importance because if you think about the history of the US in particular, one of the most influential inventions now recognized was air conditioning because it made 2/3 of the country habitable and workable. People could actually work through the summer months because they got a good night's sleep with air conditioning. And that transformed the US economy. And we can do the same across low-income countries today, but you can see that a number of things have to come together. Not only do we need air conditioning, we have much higher temperatures than the Americans. We have buildings that have no insulation, and above all, we have economies which are really troublesome at the moment in the sense that huge amount has been invested in education and in creating engineers, but these economies are still not growing in the way that we hope. So as I indicated before, air conditioning is becoming a necessity in many cities. And I've summarized there the aspects that are all coming together to do this. Climate warming, obviously, urban heat islands, urban temperatures are rising, the inflexibility of apartment-style accommodation. If you're on the 23rd floor, when it gets really hot, you can't go down to the basement. Productivity depends on sleep quality. All the new technologies that people are talking about, from phase change materials to Peltier cooling, membrane separation of moisture, and so on, these require massive technological investments, and that's not going to happen without significant productivity improvements. Productivity growth has ground to a halt, and that's a whole area of discussion which I think we'll keep away from tonight, but it's one which I study extensively. And this fact that, there's lots of interesting new building designs there, which are far more sustainable than today's buildings. And yeah, we will see lots of them being built. But we also have to realize that pretty much all the buildings we see today are still going to be there in 30 or 40 years. You have a look around your cities now and go and have a look at buildings stretched back and see how many of them have been replaced. Not many. It's too late to rebuild entire cities. We need solutions for the cities that we have today. And here's an example. This is Mediterranean architecture. These houses, these cities are going to be subjected to temperatures that we now see in South Asia, in buildings that were never designed with much ventilation or air conditioning in mind because they were built for a Mediterranean climate. Here's an example of a city, a new city constructed using the architectural idea that emerged in the 1940s and 1950s, that since we now have air conditioning, it doesn't matter how you design the building because the internal temperature can be regulated with air conditioning. So huge areas of glass and vast energy demand. Well, this is Qatar, and they're sitting on a huge gas field, so they can sit and smile, and they've got huge amounts of money. They can buy their solar panels in due course, but not everybody has that option. Now, here's some really interesting work on thermal comfort. So what is this? This is a slide. It's entitled across the top. I'm sorry, there's not a proper title. Temperature clouds, buildings in heated or cooled mode, and it's the slide number 24. So these are the preferred conditions that people have in different parts of the world with different ambient temperatures. The ambient temperature is across the bottom. On the right-hand side, we see really hot environments around 40 degrees. And on the left-hand side, we see really cold environments down to about minus 20. So obviously, northern China is on the left and Saudi Arabia is on the right. What do we learn from this? When people can regulate the temperature of the building to whatever they want, they will choose the same temperature. They all want to be at a temperature between 20 and 30 degrees. And that's a really interesting finding. And it's something new. Here's data from 1999, taken in Pakistan, that shows exactly the same information, the ambient temperature across the bottom, T out or T outside, and the internal temperature across on the left-hand side, that's the vertical axis. And we see here that the population, what it shows is green dots if people feel comfortable, red dots if they feel too hot, and blue dots if they feel too cold. And what that tells us is that people, before the age of air conditioning, when buildings didn't have air conditioning, people adapted to high and low temperatures. And they felt comfortable at temperatures which air-conditioned populations would sit there freezing cold, partly because they put more clothes on. And in summertime, they wore less clothes and did sensible things to keep cool, like drinking lots of water and had ceiling fans, and were quite happy in temperatures up to 30, even 35 degrees, which people who are used to air conditioning would be shuddering at the prospect of surviving. So what we're seeing here is that people adapt. Now, some really interesting work has come out of studies, of admittedly small studies, of adaptation. And most of this work has been on sports people who, people are going to compete in the Olympic Games. It's going to be very hot. So one of the big questions is, how long does it take for the athletes to adapt? But some really interesting things have come out of these studies. What it shows is that people who live continuously at a constant temperature in an air-conditioned environment day and night lose a lot of their ability to adapt. They lose cardiovascular condition. And so this idea of the sick building syndrome, people who work in offices and they're air conditioned during the day, air conditioned at night, they really do get sick because they're losing their ability to adapt. And this could be a very significant health issue as we go forward with more and more people subjected to these conditions. What it also shows, by the way, is that you pretty much everybody adapts to a new temperature environment in a period of about 6 or 7 days. It doesn't take that long. Now, what I'm going to go on now is show some of the solutions that are emerging. First, at the cold end. So this is work that's been done by a friend of mine, Peter Mears, who used to be with Fortescue Metals Group here in Western Australia. He has been supporting a project here in Mongolia to build properly insulated yurts with very tiny electric stoves. And the combination of insulation and localized heating has dramatically reduced the electricity consumption. The motivation for this project was in fact a health issue caused by extraordinary levels of pollution from coal-fired power stations, which pretty much generate all the electricity in Mongolia. and particularly in the capital, Ulaanbaatar, very, very high death rates resulting from this pollution. So this was a project to show how architecture, traditional architecture, can be adapted to achieve astonishing reductions in energy demand. At the warm end of the scale, this is the new architecture school at National University of Singapore. And they have achieved near net zero energy consumption with this building. And they have done that by still working inside the air conditioning standard that pretty much everybody subscribes to, ASHRAE standard. What they've done is institute an air conditioning system, and we'll see on the next slide an internal view of the building. And if you look carefully, you'll see there's a lot of ceiling fans there. Instead of cooling the air down to a temperature of about 18 degrees centigrade and then pumping it into the occupied spaces of the building, where of course it gets warmer and then eventually finds its way back to the air conditioning plant. So you've got an indoor temperature somewhere around 22. The air indoors is reduced in temperature from the outside air about 32, 33 degrees down to about 28 degrees centigrade. And some of the moisture content is removed. They call this tempered air rather than chilled air. So the energy consumption required to get the air into that state is far less than it would be to cool it to 18 degrees centigrade and reduce much more and eliminate much more of the water. The effect of the ceiling fans is to increase the air velocity to the point where people feel comfortable. So if the air was static and still under those conditions, you'd be sweating and you'd really feel very uncomfortable. But with the ceiling fans running, it becomes comfortable. In other words, restoring conditions to what you might have had in the days of Somerset Maugham. And so this dramatically reduces the energy consumption. Bear in mind, of course, these buildings are public spaces, so they are predominantly used during the day. So we have, of course, the option to use solar energy to run the system substantially during the daytime and with a much lower storage requirement than you would require for residential accommodation. So this is a very good solution for offices, public spaces, factories, and so on that are going to be running predominantly during the daytime. Now, I want to finish off the talk by talking about the idea of localized comfort. So, in fact, for hundreds of thousands of years, we've been accustomed to using localized comfort. It's called a campfire. And it's of course for feeling warm. And if you get too hot, you move a little bit further away. If you're not warm enough, you move closer to the fire. This picture here shows a bedside lamp. We use this principle when we want to have a bedroom where we only need lighting in one corner to read a book, and maybe on the other side of the bed is dark enough to sleep. As I said, I was in Pakistan when Ian was introducing me and asking those questions. I was in Pakistan thinking, how do I keep cool through the power cuts? And it occurred to me that, just a breath of fresh air on my face would be sufficient to keep me cool. Physiologically, this area, the face and neck particularly, is where we lose most of our energy in hot conditions. I should point out that keeping warm in cold conditions is physiologically very different from keeping cool in hot conditions. But by cooling the face, you achieve a sensation of comfort out of all proportion to the amount of energy that you use. And so this picture showing it in a bedroom shows one of our little air conditioners directing a stream of cool air over the bed. And this works fine in pretty much all the time in Australia. Here's another photograph showing a group of 3 people sitting on a couch, and the air is moving past them. That provides sufficient comfort, depending on, of course, the environmental temperature. If you do remember, and I'm going to repeat it just so that you do understand, in our bedroom in Islamabad, through the summer, the temperature will be 40 degrees day and night. The concrete is a very good store of heat, so it doesn't cool off at night, and it absorbs excess heat. It could be 46 degrees outside, but you can't sleep in 40 degrees. No one can. So you need more cooling and so the idea here is we developed a tent, and this tent is specially designed to maintain a layer of cool air over the the bed. I can talk more about the details if those of you are technically interested. Again, it's quite a challenge to reduce the power consumption down to 300 watts because, as you would appreciate, there's a significant amount of radiant heat coming from the walls that also has to be dealt with. But this device was designed for Pakistan. And I think if I'd approached a business consultant 5 years ago and said, "Do you think I should launch this project in Pakistan?" People say, "You've got to be joking." "How much do you know about selling?" I said, "Nothing." "How much do you know about selling electrical appliances?" "Nothing." "How much do you know about doing business in Pakistan?" "Pretty much nothing." Those would have all been red flags. But with my wife, we sat in a lounge room in Lahore with this very large pile of boxes that had just arrived from China with these air conditioners. It wasn't the first ones we deployed. We did actually do some trial ones a couple of years earlier to make sure that they would work okay. And we said, "Okay, now we got them. How do we sell them? And what do we do next?" And her response was, "Say a prayer." And now we're 5 years down the line. We're selling in 5 different countries. We've just sent our first consignment to West Africa. And we're steadily growing, but not yet profitable business. So in essence, here we have a technology which works in existing buildings. It works in the kinds of thermal environments that are common across South Asia and Southeast Asia. It is affordable by 40% of the population currently. Its energy consumption is 300 watts, pretty much constant. And that's readily supplyable from solar during the day and imposes a far lower requirement on the electricity grid at night. Across much of the time, the energy consumption, particularly with the tent, is substantially less. So we get the energy consumption down to about 90 watts per person. And I'm confident we can reduce that in future. So that's where we are. Can we reach zero emissions by 2045? Yes, I think we can. I've shown you the National University of Singapore. That building is now, those systems are now being replicated in many other buildings. But it does require substantial alteration, not only in the way the air conditioning system runs in a building, but also how people use it. And it's okay, don't worry. We have localized air conditioning, and I'm sure there'll be other devices that are around, and many other improvements. It's amazing what happens when you allow engineers the freedom to come up with ideas and you put them in a marketplace where people buy what they think works. And it's been a wonderful experience for me to bring so much pleasure to so many people who write beautiful things about our air conditioners. And when you realize the conditions that they put up with, and you use it yourself, and you realize what a difference it makes to people's lives, you have to keep on doing it. So that's enough from me now. I'm quite happy to answer questions, which I believe are going to come in by text message. Is that right?
There's been only comments, I believe, from your wife, but she's keeping you honest. So I'll join you.
I did send the link. Yeah, I did send the link to my wife. Okay, good.
So that was fascinating. And I've long been interested in air conditioning, trying to find ways to cut power demand, particularly on the system, because if you saw historically on the Swiss Southwest Interconnect system here, in years past, our peak demand was dictated largely by afternoon air conditioning. Yeah. And of course, since
I believe around 50% of our electricity capacity in Western Australia is used on 2 days a year.
Yeah, exactly. And so the peaking plants that have to be there to accommodate that, they're costly, big capacity payments, and they've got to be there when that's all changed. Yes. Of course, we're now because
it is changing. Yes,
because the duck curve and whatnot. But what I find interesting is the fact that you're able to have this unit that blows cool air on the person's face, but the reject heat just is blown somewhere else in the room, presumably.
Yeah, it's like your kitchen fridge.
Right, same.
So if you put your hand over the back of the kitchen fridge, you'll find quite a bit of warm air there.
Yeah, yeah.
So the trick here is to get the right balance.
Right.
Between cooling sensation on the front side and the warmth that obviously rises to the ceiling. So it's designed to be used with windows open, first of all.
Right.
You do get some temperature rise in very small rooms, and so we provide advice for people how to minimize that if they want to. There are tricks that you can use. And I think that the biggest barrier is to get people past the idea that the whole room has to be cool.
Mm.
You know, this is the stumbling block. And once people realize the scale of the savings, it happens very quickly. Right. So in Pakistan, the running cost is so small compared with conventional air conditioning that it's really, you don't have to push the product very hard at all.
Okay.
Same is true in Indonesia.
Right.
In Australia, it's not such an easy sell because people are just used to certain ways of doing things.
Yeah.
And, you know, my experience is that in Australia, energy consumption for most people is not the issue that politicians make out.
Right. Yeah. We have a situation here, for instance, in electric vehicles. I've got a very good friend who says, "Oh, I'd never have one of those." To my wife, she said she wouldn't want to plug it in every day. But I said, "Look, you know, if the amount of times you have to actually plug it in and plug it out, it's done overnight. It sits there quietly. New metering systems can provide a response to when it's charging or not charging. And in the future, there'll be two-way between the house and back. And think of the amount of time you've got to go out of your way to go and fill up the petrol tank every week. It's really not such a big issue. And if you were reversing it the other way, you'd have the same habitual objections. So,
you know, it really surprises me with electric vehicles that there's a technology called high frequency induction, which seems to have been ignored. And high frequency induction will allow a contact-free connection for recharging the car. It just surprises me that the vehicle manufacturers have not got onto that.
The buses are looking at that. The buses in China have got that exact system. It's non-contact.
It's being used commercially for quite a long time.
Yeah, and mobile phones now, it's getting to be quite big. All the latest phones have got that.
Yeah, so I think that inconvenience factor will disappear.
Yeah.
And particularly as we see autonomous vehicles starting to come in for suburban shopping trips and things like that, you know, the attraction for so many people not having to park the car.
Yeah, exactly. The other question I've got on the air conditioning is, you know, if you're moving around, if you're playing table tennis or you're in a snooker room or something, is it not more difficult then to orient the air conditioning, the closed comfort system? If somebody's moving around the room, if they're vacuuming the house, or, you know, they're...
Generally speaking, in hot weather, people don't move much.
Yeah. True.
So, of course, if you want to play table tennis, you need an air conditioner on while you're playing table tennis because you need a large space air conditioner. If you're going to have a party, you have a room air conditioner.
Yeah.
Personal air conditioners are not for cooling crowds.
Right.
But what we're talking about here is reducing the overall energy requirement.
Right. Now, the other thing is on the tent, the bed tent.
Yeah.
Just a question there. I've got a friend who's very big on opening windows because of CO2 buildup. How do you accommodate for CO2 buildup in the bed tent?
Clever design.
Okay. So
it is designed. Has been designed with that in mind.
Right.
Yeah. So there is constant air exchange, and so it's important to get the balance right to make sure that you get sufficient air exchange to refresh the air inside the tent.
Right.
With two people sleeping inside, and at the same time that you maintain a reasonable power demand. So that's where quite a bit of the power demand comes from. It is because you do have to recycle the air. So a lot of it is in the design of how you get the air into the tent, how you get it out, and how you control the circulation within the tent. Yeah, we've done a lot of experimentation on that.
Right. Yeah. And what about the material? Is it a plastic tent, and do you get condensation issues or anything like that? Or
condensation can be an issue. So there are design features in the tent to minimize that. There's a company which appeared for a while. I'm not sure what's happened to them. Evening Breeze. They used a canopy over the top of the bed, and for them that condensation issue was really, really difficult to solve.
Right.
They did manage to solve it in the end. But we don't get any condensation in the tent. It's actually a polyester fabric. There's 2 or 3 different kinds of fabric with a cotton base. Cotton base is washable.
So it's a bit absorbent. Yeah.
Yeah.
Okay. And then the other thing is, of course, it seems to me that mosquito prevention would be a great thing as well.
Yeah, exactly. Yes.
Yeah. It's a big benefit.
That's a big selling feature, and protection from dengue, particularly.
Right.
Across Asia is a big issue.
Yeah. Right. So managing peak demand in the third world would be this is a big step forward. It might mean that if more of these units are used as people get wealthier, because we know the third world is getting, they're getting away from poverty. So electrification and use of air conditioning that's never been part of their cultures before. This is going to have a big impact on decarbonisation and also the ability for these places to have less power.
We think so, yes. Yeah. And certainly as new battery technologies come along for stationary storage, particularly, as we can use more renewable energy, then keeping energy consumption down obviously makes all these technologies far more affordable.
Right.
So that's the whole idea. You can use the same amount of electricity to keep an awful lot more people comfortable.
Right. And do you see these? A lot of people through the night, you cool down. When you first go to bed, you're actually quite hot, and then 2 or 3 hours later, I used to live in Singapore and used to have the fan on, and it was actually too much at about 3 or 4 o'clock in the morning because your body cools down. You see that as something that you're factoring into?
Well, it's really interesting, and I'm not a physiology expert, and we don't pretend to make prognostications about the physiology of people sleeping and so on. All our development work has been done ultimately by trying it out with people and asking people what they feel like. So I got this great feedback from a fellow in Singapore who has an extremely conservative father, and his mother, who accepted the machine, said, he's never going to use it because he has been used to the idea all his life that he ons the air conditioner at 8:30 and he offs it at 10:30 because then it gets too cold and dry, and then he opens the window and by that stage he's ready to go to sleep. She said, you know what happened? He on the new air conditioner, and he didn't off it. He said, this is so good because I feel comfortable. I don't get that horrible dry and cold feeling that I get with normal air conditioners. He said he woke up at 7 o'clock in the morning and then he turned it off. And he's used it every night since. He's just switched like that. I never thought he would do it. This is the kind of transformation that we've seen in people who try it.
I love the way you use the Singapore colloquialism of I on it and I switch it. I don't say switch it on, I on the switch.
There's a question coming.
Oh, a question coming. Okay,
right.
let me take that one.
Okay,
one from Rob Meacham, one of our members, has been on our committee last year. He's in charge of running a policy group. So he thanks you, Professor Trevelyan, for your wonderful presentation. He's asking, is it possible to channel the heated air from the small air conditioner to the outside of the building at modest cost?
Good question. So you would have seen portable air conditioners with a big ugly pipe at the back, which does exactly that, or it's supposed to. So the pipe is supposed to take the warm air from the backside of the air conditioner and send it out through the window. Right. But when you actually work through how these things operate, and actually it took me years, thinking about it. I knew there was a flaw in here somewhere, but it didn't occur to me. So it's really hard for most people to understand. Because you're sending air out through that pipe, air has to come back in. And it's going to come in mostly through the roof space, which is the hottest part of the building, come down through the light fittings. So what do these machines do? They suck in air from the room, which of course is adding to the amount of air sucked in from the outside. They cool it. The cool air comes out, goes back in, is sucked in by the machine, and the machine sucks in much more air than it cools and heats it and throws it out the window. And you have to say, whoever thought of such a crazy idea? Now, this causes headaches for regulators because they're extremely energy inefficient. Very, very inefficient machines because they run at full power all the time. They don't pull the temperature of the room down very much. So in the US, what they do is they derate the cooling capacity. So the actual coefficient of performance is so low that most people say, okay, I'm not going to buy one. But here, there was an attempt to give them a mandatory 0-star rating under the new energy labeling rules, which come in, I'm not quite sure when, they're supposed to come in when the Council of Australian Governments finally puts their act together. The importers got together and lobbied the politicians to make sure that change wouldn't happen. So it's a matter of educating people about how expensive they are to run. Most people do actually understand the simple argument that they're extremely expensive. And when you point out, well, you can get the same degree of comfort for a fraction of the price. And I think, look, this is the big argument about sustainability. We really, the great challenge, and I think that we can do it, is that we can come up with sustainable solutions which are cheaper all round. So when you think about it, the cost of modern buildings largely reflects the challenges of air conditioning.
Yes.
Right? Modern buildings are extremely expensive because you want them to be air conditioned. Right? When you can air condition a fibro shack or a bamboo hut, how many people want to spend? Well, there are always some people who want to spend $5 million building a really, a palatial home. But for lots of people, a bamboo hut is fine, especially if it's air conditioned.
Yeah, that's a fair point. Yeah.
So we actually use there's a lot of indirect costs associated with air conditioning.
Yeah, I can see that. Yeah. Okay, let's see if there are other questions. Okay, so there are window fittings that allow exhaust air out. Hairdressing salons and nail salons in small rooms sometimes use them. I guess we'll take that as a comment.
Yeah, thank you. Exhaust fans have been around for a while. They work really well.
One from Kate Bolland, who's our secretary. What will happen in those massive high-rise apartments all over China? Millions of conventional air cons will be retained?
Well, that's a good question. We'll see. And there are lots of different approaches. One of the issues, China is very different everywhere else. One of the pressing issues in China is floor space. And in China, across most of China, you need something which provides warmth in winter as well as cooling in summer. So probably they might well stick with them. But they'll generate their electricity a lot more efficiently.
Yes. And
they will use different refrigerants. What we're talking about, the big area of growth that's in the hot parts of Asia and right across Africa. By the way, that data that I showed does not include Africa, because at the time the work was done, nobody thought that Africa would really develop economically the way that Asia has. Well, now development is surging ahead across Africa, and we're going to see growth in population and energy consumption across the African continent.
Right. Yeah.
So it's like we've got to adapt different technologies to different places.
Different markets. Yeah. And with climate change, I guess we're going to see the hotter areas are going to become unbearable. Refrigerants might even be challenged, right? The types of refrigerants that will operate in some of the worst places.
No, I mean, refrigerant technology can deal with it. You have to select the right combination, get the right mechanical design correct for the application. But the key to it is to find clever ways that reduce energy consumption, reduce greenhouse emissions, and above all, are cheaper.
Yes.
So that people realize that this is something which is cheaper, it's healthier, it's a better way to live, it's more flexible, it's more enjoyable, and people will look back and say, why did they take so long to change? Why did they stick with those terrible technologies for so long?
Yeah. And we could apply that to many technologies in our modern world.
Exactly.
These horrible internal combustion engines with dreadful emissions and poisoning us all. And here we are in the middle of a pandemic, and we're saying, hey, we need to get through this. We'll throw as much money at it as we can. And yet we're not prepared to throw money at a bigger issue than a pandemic. We're talking about potential extinction event. And we're thinking about markets first. It might be a wake-up call.
It might be a wake-up call. Yes, let's hope it is.
So, right, I'm being told by our faithful Margot that it's time to cut.
How many questions that we haven't answered? Probably about 200.
Oh, I'll say, okay, so there is one here, another one. It's thanks for the presentation, Professor James. Sorry if you already mentioned, what is the COP of these units? Is there much potential to increase it, or is it close to the limit? For the benefit of those that don't know what COP is, it's the coefficient of performance, which is related to how much energy you put in and get the thermal energy cooling or heating out.
I'll give a very quick answer. It's around 3. Yes, we can improve it a little bit, but getting that coefficient of performance in a very small package has been, again, a big technical challenge.
Yep. So the answer to that is 3 around, and with the potential to improve. Another one is one of the reasons for not changing to low RF refrigerants that the car companies, etc., using proprietary refrigerants don't want to lose the income stream?
I don't believe so.
Hmm.
No. I mean, look, we have seen the Volkswagen and similar cheating scandals amongst car companies. We do know that they collectively try and cheat the system when they can see an opportunity to do so. So I wouldn't rule it out. But at the same time, you have to understand the vast majority of engineers want to do the right thing.
Right. Yeah. And on as an extension for that, the refrigerants you mentioned earlier, potentially flammable. Were you referring to propane? Because I know that was one of the ones.
Propane, isobutane.
Isobutane.
Yes.
Okay.
Yeah.
So you see them as the next generation for small air conditioners?
Yeah. The safety issue is such that you have to keep the unit small. It doesn't, for personal air conditioners, it's not an issue.
Right.
But for split system air conditioners, it's a major, major headache.
Right.
And so various companies are experimenting with different ideas. For example, having all of the refrigerant in a small compact unit on the outside of the building, and then using piped chilled water.
Right.
But of course, there are efficiency losses in doing that. But it is, as your choice of refrigerants comes down and cost becomes an issue, maybe that's another way to do it.
Great. We are out of time, so Professor James Trevelyan, thank you so much for your very, very interesting presentation. Far more interesting than I thought it would be. And
thank you.
So we'll be interested to hear more questions that may come in, and we'll certainly pass them on to you. If you have any other questions, please fire them in, and we'll be able to get James to answer them and put the answers up on the screen.
I do have a paper which I'm quite prepared to distribute on a needs basis if anybody wants it. It has not been published yet.
Okay.
So I don't want to publish it at this stage for various reasons, but I'm quite happy to send out the draft manuscript if anybody's interested in the detail and references.
I'm sure it will be. Okay. Thank you, James, and thank you for our audience, and we'll see you next time.
Thank you for the team behind it. Thank you, Alistair in Melbourne.
Yeah.
Thank you, Margot.
Yeah, thanks to everyone.